The next couple of lectures, we're going to look at strictly hyperbolic systems. So these are equations that have advection in them only, without any diffusion. Thankfully, in reality, most processes have diffusion in them, and diffusion tends to take care of oscillations. But still, when you're thinking about hyperbolic systems, and historically, hyperbolic systems were really important in the development of aerodynamic flows and compressible flows with the Euler equations that are inviscid. And so trying to solve the Euler equations with standard hyperbolic schemes for advection resulted on all sorts of weird things. So I'm going to lay out these slides in a historical fashion. And then, lead you all the way to what I call the flux revolution, or the advent of nonlinear schemes. So remember that the Navier-Stokes equations consist of transient, advective, diffusive, and source terms, linear and nonlinear. And we talked last time about the character of partial differential equations based on their characteristics. You have hyperbolic, parabolic, and elliptic types of equations in general. The Navier-Stokes equations behave as hyperbolic, parabolic systems plus an elliptic requirement for mass conservation. But today we're going to focus only on hyperbolic equations. And a classic hyperbolic equation is the constant speed advection equation given by this. du dt, partial u partial t is minus c partial u partial x. We call c the advecting velocity. That is like a bulk transporter that is going to take a quantity u and advect it. It's in its simplest form, you're taking an initial condition and just moving it in space along the characteristics. Now we understand what that means. So du dt, total derivative equals 0 along the characteristics x naught equal x minus ct. Okay? Now, advection comes in two flavors, linear and nonlinear. With linear advection, you have a constant advecting velocity, and that's just going to move things along. With nonlinear advection, if you have stationary points or positive and negative values of the function, you will notice that a key difference between nonlinear advection and linear advection is that the advecting velocity is a function of the quantity. So if the quantity is positive, this is going to move it in this direction. If the quantity is negative, it's going to move it in the opposite direction. And this is how you develop shocks. Okay, this is an example of what would happen in the Burger's equation, for example. And what I have here down here is the viscous Burger's equation. So I'm adding a diffusion term to stabilize the numerical solution. And you see how we quickly form shocks or steepened waves. Okay. So let's look at some first-order schemes, which we're familiar with for the constant speed advection equation. We'll start with the, we'll start with the Upwind scheme that we all know and love. We've done this for the last 3 months, and we know that this scheme is conditionally stable. In 1D depends on the CFL condition given by the Courant number, c dt by dx should be less than or equal to 1. But what does the Courant condition mean? This is an aside. The physical meaning of the Courant condition is explained as such. If you have a signal on a grid like this, so this is the signal given by these points at these discrete coordinates. If this signal is moving at speed c, right? That's the governing speed of the equation. So that signal is moving along the grid at speed c. So in a single time step, small delta t, this signal is going to move by an interval del x, okay? This small delta x. The CFL condition tells you that this interval, delta x, cannot be bigger than the grid spacing delta x. So del x cannot be larger than the grid spacing. In other words, you cannot move information more than one grid point at a time. Okay? We know that this scheme is very diffusive, but it is stable and it works. And when you're testing a numerical code, just test it with Upwind. It's pretty robust. You know, it adds very desirable diffusion, and typically you can get good results. But oftentimes that's not what we want. We want higher order schemes. So we'll talk about this a little bit later. Okay, and last time I discussed how we can generalize the Upwind scheme in the presence of a non-uniform advecting velocity, or an advecting velocity that changes in space, goes positive and negative. So we know that if at point I the speed is positive, then we're going to go with backward differencing. That's the Upwind, right? And if at point I the speed or the velocity is negative, then we're going to go with forward differencing. It's still the Upwind. It's picking the Upwind value. Okay, so you could go and implement this and do a bunch of if statements, but there's a more elegant way to combine the two when you know you have varying velocity. Like in a two-dimensional case with the Navier-Stokes equations, you may have positive and negative velocities. So how do you combine the two? You can go and do if statements and loop over the faces and check if the velocity is positive, then do this or do that. Or you can combine things very elegantly as such. You can define C plus and C minus as 1 over 2 for C plus, 1 over 2 C plus absolute value of C. So in terms of Python, you take the entire array of C and just form another array called C plus, which is 1/2 Ci plus absolute value of C. And then C minus is 1/2 Ci minus absolute value of Ci. And then you combine both upwinds, or both the backward and forward difference, as such. So when Ci is positive, this guy is 0. C minus is 0, and this term disappears. Okay, so this is a combination, C plus times backward difference plus C minus times forward difference. When C is positive, we want to pick the backward difference. This guy goes to 0, so this guy disappears, and we're left with the backward difference. If Ci is negative, then what happens? These guys disappear. You get minus plus, right? And then these guys become a minus Ci, and you plug it in here, and you pick the forward difference. Okay. Here's an example of a varying velocity profile. So you have an initial condition that looks like this, a bunch of sine waves added together, subject to the advection equation such that the speed is a function of x, looks like this. So points over here are going to move in this direction, and points over here are going to move in that direction. This is an animation of what happens using that generalized upwinding. Okay, as expected, they spread apart. This point at speed equals 0 doesn't move. Okay. Now a cool thing happens when you do this. When we combine the two, if we go and substitute C plus and C minus into this equation, what do you get? You get a clear description of the numerical diffusion introduced by the Upwind scheme. So what you end up having is un plus 1 is un minus a central discretization, which we know is unstable, plus a stabilizing diffusion. Okay, and you see that the coefficient is always positive here by the presence of this absolute value of C. So that explains how, in other words, the general Upwind scheme is a central scheme plus a diffusion term, okay, to stabilize the oscillations that come out from the central discretization scheme. Okay. Now, there's another way also to generalize the Upwind schemes used in the finite volume community. They define the symbol, the double absolute value, as the maximum of A and 0. Okay, so if A is a negative quantity, then you pick 0. If A is a positive quantity, you pick A. Okay, so then what happens in this case? You combine, and you also combine with a backward difference and a forward difference. But notice here the challenge is that you have a minus double absolute value of a minus Ci. Now you can run the exercise in your mind and verify that this is going to return forward or backward depending on the sign of Ci. Another classic scheme is the Lax-Friedreichs scheme, which starts by taking a central differencing formula, and then so un plus 1 minus un forward Euler in time, central in space, and then we take the old derivative, okay, and turn it into an average of the values straddling point I. Okay, so once you do this, you get this scheme and you get this modified equation. The problem with this scheme is, well, it's very diffusive, but it's also conditionally consistent. Because the order of accuracy, remember when we were talking about numerical and truncation errors, this scheme is inconsistent. In other words, it will not return the governing differential equation unless delta t is equal to delta x. So if you pick delta t equal to delta x, then it will become consistent. Okay, but first order schemes, we want more accuracy, and they're diffusive. And trying to capture very sharp shocks in 2 or 3D, they're going to smear everything about that shock. So we want the higher accuracy that will give us better representation of the shocks. Okay? But what happens with high order schemes? The first scheme, forward in time, central in space, we know it's unconditionally unstable, so that doesn't work. So we know that for central schemes or higher order schemes, we probably have to change the time integrator to give us better stability, okay, to see if we can get rid of the instability. Now, instabilities typically start with oscillations, and then they grow unbounded, okay? So then you get to the backward in time, central in space. That is unconditionally stable, but it's also dispersive. And we've done this before. This results in a tridiagonal system. But what I'm interested in is explicit schemes that are also higher order in time. So that gets us to the leapfrog method. And what I'm showing here is just a survey of the methods. And I'm going to show you an implementation of some of these and show you how quirky they are. But this is just a historically, those were important in the development of schemes for advection. So the leapfrog scheme takes a central derivative in time, so increases the order in time, and keeps a central discretization in space. So that makes the central scheme stable, because now we've changed our stability characteristics, okay, for the time integrator. The modified equation, as you can see, is very dispersive. You have this dispersion term, and lambda is the Courant number, okay? This is still stable for CFD conditions. It's really bad dispersive for shocks and sharp interfaces. So for smooth functions, all of these schemes work okay, all right? But once you are thinking about shocks or things like compressible flows, you cannot tolerate dispersion. Okay. Another scheme is the first Lax-Wendroff, which is for linear equations. So what they do, they essentially take a Taylor series of un plus 1 around un, so that's ut plus delta t around ut, and that gives you these guys. And then what you do, you take the advection equation and say, since ut is minus cux, so we're going to substitute this ut by minus cux, and we're going to substitute utt by c squared uxx. And once you substitute, you get un plus 1 is un minus c delta t ux plus delta t squared uxx. And then you just use central differencing for all of these guys, and then you get the first Lax-Wendroff scheme. That gives you second order in space and second order in time. So delta t cubed is local order of accuracy. It's actually globally second order. But the modified equation tells us this scheme is dispersive. And so for sharp signals, you're going to get a lot of dispersion for the Lax-Wendroff. There's another Lax-Wendroff scheme where it's kind of a little bit quirky. You split the first Lax-Wendroff into 2 steps, and you time step to n plus half. So take a half time step, and you take the old derivative and kind of do this average, ui plus 1 plus ui. This is a forward difference, or a forward, this is like a phase value, actually. This is just like a phase value. And if you do these steps, both Lax-Wendroff 2 and Lax-Wendroff 1 are equivalent for linear equations, but for nonlinear, this behaves a little bit better. And you can test these, I'm not going to worry about it. And finally, the McCormick scheme, where you do a prediction using just a forward Euler method with a forward difference, and then you do a corrector with a backward difference. So you're combining upwind and downwind, or downwind and upwind, okay, with the predictor and correctors in an effort to kind of average the error out. And you can try this as well. I have a couple of schemes implemented here for Lax-Wendroff, Upwind, and the leapfrog. And look at the leapfrog. It's insanely quirky with sharp signals. I can actually believe that this would result from a numerical solution, but it does. The Lax-Wendroff is dispersive, and the Upwind is diffusive. We kind of know that. But all of these schemes were developed, and it was like, you know, the dark arts. How did they come up with these schemes? Let's try this, let's try that. There's no kind of general reasoning behind this. The modern view takes a different perspective. And it leads us to a way to design high-order schemes. We're going to need high order in time, and I'll show you why. Well, actually, in the homework, we're going to prove why. But if we want to get high-order schemes, when I say high-order schemes, I'm focusing on space now. So second order, third order, or higher. Okay? And to do this, we need to return to the finite volume formalism. Okay? And like I said, you know, over the years, there have been a ton of schemes: leapfrog, Lax, Wendroff, McCormack, etc. Most of these are based on finite difference formulations, but the modern view requires a finite volume formalism. But first, let's talk about conservation forms, because we are going to prefer to solve the equations in conservation form. Okay? And the conservation form is going to take whatever first derivative you have over here and turn it into a flux form. So for example, if you have u du dx over here, that's d by dx of 1 over 2 u squared. That's the Burger's equation. Okay. For a constant speed advection equation, the flux is c times u, or cx times u, however you want to put it. For the diffusive flux, you write it as mu du by dx and the derivative. So that takes us back to the finite volume formalism. But what are the benefits of conservative forms? Okay, we talked about this a long time ago, but now we're going to show you, illustrate to you just one way that conservative forms are superior to non-conservation forms. All right, so we're going to take this equation, and this is exact mathematically. We're going to take the integral over the domain. So we're going to integrate du dt dx over the entire domain over L, and df dx over the entire domain. So that gives us the integral of du dt dx plus f at the end minus f at the origin equal to 0. Okay? And if we further impose no flux at the boundaries, or if we impose a known flux at the boundaries, okay, what we expect for this equation, in this case when the fluxes are 0, we expect that the integral of du dt dx over L to be equal to 0. And if this is the case, we call u, we say that u is conserved. Okay? So let's see what happens if we solve the following equation, the Burger's equation, using the two different forms. Okay, so I'm going to take the Burger's equation. This is the non-conservation form, and this is the conservation form. In multiple dimensions, this is the divergence of a flux. Okay? So if you remember one of your earlier homeworks, when I asked you to write it in conservation form, tie that homework to what we're going to show you right now. So mathematically, we expect these to be equal. Okay? But numerically, they are not. So on a finite difference grid, we're not even talking about finite volume yet, just looking at conservation forms. The discretization at point I for this guy, if you're, let's say you're doing, we're upwinding and u is always positive. So this guy is ui times ui minus 1 over delta x. That's not equal to this guy, which is 1 over 2 ui squared minus ui minus 1 squared over delta x. Okay? So what does this mean? All right? Mathematically, we expect these guys to be equal, but they are not equal numerically. So let's take this guy and do the integral of u du dx. Remember, this is the integral of the flux. And if the fluxes at the boundaries are 0, this integral should be 0. Right? We just showed this a couple of slides ago. Right? So if you remember, right here in this slide, that this integral if the fluxes are 0 at the boundaries, it should be equal to 0, or the difference in fluxes. Okay? So let's see what happens numerically. For the non-conservative form, if you take the integral over L, u du dx, that's approximated as ui dui dx times delta x. Assume so delta x and delta x cancels out, and you do the multiplications. This is not necessarily 0. So you lost your conservation property if you're using the non-conservation form. Okay, so you can carry out this summation, okay, and this is not necessarily equal to 0. But if you take this form, something beautiful happens. You get these alternating terms, u1 squared minus u0 squared plus u2 squared minus u1 squared. So u1 squared and u1 squared disappears, and then u2 and u2 disappears all the way, and you are only left with un minus 1 squared. So that's the last point, minus u0 squared, but the fluxes are 0. This is the flux, right? U squared is the flux, and the fluxes are 0, so that's equal to 0. And you conserved your quantity. See the power of the conservation form. So it's a highly desirable property, and it's generally believed that conservative discretization, conservation forms are superior to non-conservative forms. But for shock waves, and that's really important, we're guaranteed to conserve shock speed, to not mess up with the speed of the shock. Now, another way to look at this is, let's take this this shock, for example, and subject it. Let's say you want to compute. This is the initial. This is state at state n. These are points I minus 1, I plus 1, and you want to advance this in time. Let's just take a single time step. Okay. With the non-conservation form, what you get is, if you're doing forward Euler again, un plus 1 is un minus delta t over delta x, ui times ui minus 1. Now, ui is 0, right? Ui is 0. That's value 0. So the whole thing is 0. So what happens is the shock is not going to move. Actually, your shock will not move at any point, even if you take point I minus 2 or I minus 1. Your shock is not going to move, okay? But if you look at it from the conservation form, and you do un plus 1 is un minus 1 over 2 delta. This is 1 over 2 delta t, and then you do the backward difference. Well, this guy is 0, but ui minus 1 is 1. And so what you get, delta t over 2 delta x. You get motion of the shock. Okay? All right. That's an aside about the superiority of conservation forms. So whether you like it or not, we're going to be using conservation forms from now on. Okay? So now the next step, since we said we need the finite volume formalism, and I haven't specified how we're going to use the finite volume formalism, let me just remind you how we do the finite volume integration. If you are taking a cell C with, this is 1D for illustration purposes, with a west and east face, you are taking this equation, d phi dt equal minus d phi dx, f df dx. F is the flux. In this case, it's given by u phi. Could be something else, okay? But it's just a flux, in this case given by u phi. Now, the finite volume formalism tells you you're going to integrate over the volume, so integral from west to east of d phi dt dx, and integral from west to east of df dx dx, and then you're also going to integrate in time, right? So then you have another integral from tn to tn plus 1 of this whole thing times dt, right? And integral tn to tn plus 1, this whole thing dt. Okay, now remember, with the finite volume method, now there's one more thing that we need to assume, and that's actually true in practice, that we know the phase velocities. Okay, and you can just interpolate the phase velocities. If you don't know them, just take a simple second order interpolation, and you'll be just fine. Okay, now for the finite volume formalism, we say that we're only going to track the average value of phi in the cell. So we're going to call that phi tilde, okay, and define it as the average value of phi in the cell. What is the average value of phi? It's 1 over delta x times the integral of phi dx, right? In 3D, this is 1 over delta v, the integral over the volume of phi dv. Okay, so that's just phi tilde. So in other words, this entire integral over here, you take the spatial integral inside, that gives you delta x times phi tilde. right? So what happens here is that you get a delta x phi tilde, and you have a d phi tilde by dt. So we're just, in other words, just tracking the average value of phi over time. We haven't done the time integral yet. Now, in this, what happens to the right-hand side, df dx dx, dx cancels out, and you get f east minus f west, but the integral from tn to tn plus 1. Okay? Now, we need to assume, just like we assumed an average value in space, we're going to assume an average value in time. Okay? So the average value in time for the fluxes, I don't need an average value in time for this guy because dt and dt cancel out. We get phi n plus 1 minus phi n. But for this guy, we don't know. We need to take an average value for f. So we call this f tilde, the average value of in a time interval. So think of time as a cell, right, just like this one. It's 1 over delta t, the integral t to tn plus 1 of f dt. Okay? So then using f tilde, we can get rid of this integral. Okay? So what that does, it gives you phi n plus 1 minus phi n tilde. In practice, we just call it phi. Okay? But you have to remember that that's just an average value in the cell, stored in the center. Okay? Minus dt dx, some average value of the flux at the east face minus an average value of the flux on the west face. Now you could say the average value is equal to the previous time value. So that makes it f east at n minus f west at n, and that gives you the forward Euler method. Okay, but we know that, and I'm kind of preempting this, we're going to need higher order time integrators for higher order spatial discretization. So I'm not going to choose f tilde to be fn. I'm actually going to do something better for that, and I'm going to take the midpoint rule. Okay, and for the midpoint rule, this says that the integral from a to b of f dt is simply delta t, or b minus a, times f at the midpoint value. In other words, this integral turns into delta t times f at n plus half at a time level in between. That's just the midpoint rule. Haven't done anything crazy here. Okay? You can do higher order, but the midpoint rule is going to be good enough to give me second order accuracy in time. Okay? Is this clear? You know the midpoint rule. The integral from a to b of f dx is b minus a f at a plus b over 2. Okay? So it's the interval times the midpoint value. Essentially, you're approximating like a little rectangle centered at the midpoint. And so what happens then, f tilde becomes f at n plus half. Okay? That's the midpoint rule. So that gives us this scheme. Phi n plus 1 minus phi n is minus dt dx, f east at n plus half minus f west at n plus half. But how do we get n plus half? We do a predictor corrector method. So we take a half a step at n plus half. We compute phi at n plus half is phi old minus dt over 2. That's a half step. And this is going to be fn and fn I minus half. Right? That's a good approximation for the predictor. And then we correct and say phi n plus 1 is phi n minus dt over dx, fn plus half east minus fn plus half west. Now, what is fn plus half? It's a function of phi n plus half. Remember, because f is equal to u times phi. So fn plus half is u times phi n plus half. Okay? Great. And that's going to give you second order. All right. Now we're done with the time integrator. We can finally get to how we design higher order in space schemes. Rules for the road. Just like we assumed a profile or an approximation for the integral in time, we said we're going to choose the midpoint rule because that's going to give us better accuracy, and that assumes a certain profile in time. The way to get higher order fluxes in space is to assume a profile for phi. What we are advancing in time is the average value of phi, but we haven't said anything about how phi changes in the control volume. So we can make it change any way we want as long as its average value is the average value, right, is equal to the value in the cell, right? So, or in other words, given an average value of the cell, we can make phi change in any way we want. So we could choose a line or a parabola or like some weird polynomial or an exponent, whatever you want. And this is how we're going to accomplish high order schemes, okay? So rules for the road, we're going to assume a profile for the variation of phi within the cell. This does not change the fact that we're storing the average value on in the cell. It only says, hey, phi, the true phi, changes this way inside the cell, such that its average value is still equal to the average value. But we can make it change in any way we want, okay? Now, given our knowledge, there's one more thing that we need to do, to keep in mind, is that we want to be upwind biased. Because given our knowledge of advection and characteristics, we know that if we choose to involve the future points, it's not going to work. Okay, we need to involve only the previous points or the upwinded points, or be as upwind biased as possible. We may choose one downwind point if we want, but we better compensate with that with many upwind points. Okay, now I need to introduce a general nomenclature because obviously the upwind direction is going to change I plus 1 and I minus 1. I'm going to get rid of the I plus 1, I minus 1 nomenclature, and I'm going to use upwind, downwind, upwind, upwind, downwind, downwind, etc. Okay? But first remember, in a given finite volume setting, this is one way to describe it. We're looking at cell C, and then you have east, west, east, east, west, west. But I'm going to get rid of that, actually, and introduce the following general nomenclature. Okay, let's start with the figure above. In practice, you're going to go and compute the flux at a face, okay? In more general codes, you loop over the cells, and for each cell, you loop over the faces, and for each face, you construct the flux and store it. So that puts us here. You are at a face, okay? And then the first thing you ask yourself, what is the velocity direction in this face? Are we positive or negative? Okay. In either case, what we're going to denote is the following. We're always going to denote the upwind cell as C. That's the donor cell. The far upwind as U, and the far, far upwind as UU. And we're going to denote the downwind cell as D, and far downwind cell as DD, etc. Okay? As we construct these profiles, you will see that this is a brilliant nomenclature because then I don't care what the direction of the velocity is. I can just pick one figure and then implement it, and I'll get the correct answer. Now, again, if your phase velocity, now forget about this figure, take this figure. If your phase velocity happens to be negative, we said the upwind cell is C. So that puts C over here, right? And the far upwind is U, and the far, far upwind is UU, and the downwind cell is the one next to it and the one behind it. Now you can overlay an I plus 1, I minus 1 grid on top of this and get your indices correctly. Okay? But this grid, the beauty of this grid is it changes symbols based on the direction of the velocity. Okay? So what we're going to do is just going to focus on this one because it's just easier to deal with a velocity in the positive. But all the answers are going to, when I say your phase value is phi d plus phi c, it's the same. It doesn't matter. Okay? It doesn't matter because we're referring to downwind and upwind. We're not referring to I plus 1 and I minus 1. When you look at textbooks, it's going to drive you nuts. You go to the Wikipedia article on flux limiters, you're like, okay, what is I? What is I plus 1? What is the velocity is negative? It's not going to make sense. So this is very beautiful. Actually, this nomenclature comes out from the finite volume community. So my master's advisor from the American University of Beirut, he actually was part of developing this nomenclature. They have a book on finite volume methods. I'll point you to it a little bit later. Okay, so with this nomenclature, let's look at what the upwind profile does. Okay, so again, we are at this face F, and we're trying to compute the flux at the face F. So capital F at this face, or u times phi f, okay? U is known, so all we're after is phi, okay, phi f. So what is the phi value at this face? Well, we're upwinding, so what we're going to do, essentially, we're going to take the value of phi at the upwind cell and just donate it to the value of phi at the face. And that's the upwind scheme. It says phi f equal phi c. C is the upwind cell. I don't care if it's I plus 1 or I minus 1. It's just the upwind cell. You figure that out in the code. Now, in practice, what I would do, if I overlay an I plus 1 and I minus 1 grid nomenclature, remember, with the I indexing, you're always increasing in this direction, okay? But with the symbols, you're changing directions, okay? So if you're computing the face value over here, or the face flux, that's going to be u times phi, okay? So we're saying if uf is positive, if you are upwinded, then take phi I. So that's u plus phi I. Plus, if you are negative, that's going to pick the upwind value. So that's going to be I plus 1. Okay, and that's how you translate from this to this. Okay? All right. So upwind is not high order for sure, right? But it's just an illustration to introduce you how we're going to use the nomenclature. Let's see how we derive the central scheme. Okay? So what the central scheme does, it essentially assumes the following profile. It assumes that phi changes linearly between the upwind and the downwind cell. Okay? And then what you do, you say, okay, I'm going to assume that phi at the face is, or the phi profile is phi of x, and that's equal a naught plus some slope times x minus xc, okay? X, the upwind value, okay? And we are trying to find a naught and a1, right, to get that slope, all right? So then you say, I want phi at xc to be equal to phi c. That gives you a naught. And you want phi at xd to be equal to phi d. So that's going to give you a1. So it gives you a naught is phi c, and a1 phi downwind minus phi upwind over xd minus xc. So that's for a general non-uniform grid. And that gives you, then once we know a naught and a1, we can apply that profile at the face. Now, if we are equally spaced, what happens? You get the central scheme. If we are on a uniform grid, we get the average value. Now, the way you think of the average value, you don't say phi I plus phi I plus 1. It's phi upwind plus phi downwind over 2. That's how you think about it. Okay? So then in practice, what you're doing is simply taking, if you are using the I and I indexing, your flux at the face is ui plus half, that's the value of the velocity at the face, times phi I plus 1 over 2. Phi upwind plus phi downwind over 2. Okay? All right, now we're done with the spatial terms that we know. What about the second order upwind? So we said we want to be upwinded. We know the first order upwind works. Why don't we do a second order upwind? So for the second order upwind, I'm going to draw a line between phi upwind and phi far upwind. So I'm going to take two upwind values. Okay? I'm going to take two upwind values. I'm going to draw a line between these two. And then that assumes also a line, a straight line that looks at a naught plus a1 x minus xc. We want phi at xc to be equal to phi c. So that's going to give you a naught. Okay? And we want phi at x upwind, far upwind, to be equal to phi upwind. So that gives you a1. And you plug things in. This is what you get. For a uniform grid, you get phi at the face equal 3 over 2 phi upwind minus 1 over 2 phi far upwind. So keep this in mind. This is phi upwind and phi far upwind. If the velocity changes, then phi c is going to be this guy minus 1 over 2 that guy. Okay? So that gives you second order upwind. And if you want to implement it in practice, if the velocity is positive, then that gives you phi c minus phi u. So phi I minus 1, 3 over 2, minus 1 over 2. But if the velocity is in the opposite direction, it's negative, then what you get, this becomes the upwind cell, and this becomes the far upwind cell. This is how you get your numbers, okay, your indices. But this nomenclature, man, it's bulletproof. Doesn't care about your indexing. As long as you change what phi upwind and phi downwind are, okay? So if you are reasoning on a grid, this is the grid for this kind of velocity. If you swap the velocity, then C is here, U is here, D is here, and DD is down there, okay? Okay, can we do even higher order? All right, quick. You've heard of quick in Fluent or COMSOL. Quadratic upwind interpolation for convection kinematics. Kind of fancy, right? All it does is assume a parabolic profile, okay, that is slightly biased to the upwind direction. So we're going to take 2 points in the upwind direction and 1 point in the downwind direction, okay? And then we're going to fit it. We're just going to fit it. And we're going to fit it. The fact that we fit it to the average values is going to return the average values if we integrate it over the cell, okay? So you assume that phi of x is a0 plus a1x plus a2x squared. You do all your conditions, okay? And then you have 3 equations and 3 unknowns, right? So a0, a1, a2 are the unknowns, and the values at the upwind, far upwind, and downwind. And then for a structured uniform grid, this is what you get. Now, when you go look at the quick implementation in terms of I and I plus 1, it drives you crazy, okay? Think of it this way. Because whatever phase you're at, you may be at I plus half or I minus half, it doesn't matter. If you're here, then this is the upwind, this is the far upwind, this is the downwind, etc. You just overlay an I grid on top of it and do your reasoning for the indexing, okay? And I just wrote down for you what would happen if the velocity is like this. Then you're going to get, remember, phi upwind plus phi downwind minus phi downwind minus 2 phi upwind plus phi far upwind. That's if the velocity in this direction. If the velocity is in the opposite direction, this is what you get. This becomes upwind, this becomes far upwind, and this becomes downwind. Okay? Bulletproof. Okay. Yes?
So how would you go about choosing what functional form connects you?
We're gonna see that none of these work because they're all dispersive. That's the bottom line of all of this, unfortunately. Okay, but this is the historical development of. So what we're looking at here is, okay, the dark arts of designing the McCormick and the Lax-Wendroff methods. Like you can't, you spend a lifetime trying to figure that out. This is a rational way to construct schemes. You can develop your own, but I'm gonna tell you that whatever you do is always gonna be oscillatory. It's not gonna matter. Okay, so that's gonna lead us to flux limiters. Okay. All right. So there's one other scheme called the from scheme. And what they do, they draw a line between the far upwind and the downwind cell. Okay? And then you take that slope and make it parallel, make a parallel slope between phi upwind and the face value of phi. And when you do this, this is what you get for the from scheme. Okay? All right. Phi upwind plus phi downwind minus phi upwind over 4. Okay. All right, so all of these schemes are fun and nice. It turns out we can generalize all of them and put them into one generic form that we call the K-schemes. And the K-schemes are, so if you notice what we've been doing, we're trying to find the slope at the face. In the end, that's what we're caring about. If we know the slope of phi at the face, we can deduce phi. Because using the slope, you can say phi at the face is phi at the upwind cell plus delta x over 2 times the slope. So if you know of a slope at the face, whatever that slope comes from, you can determine the value at that face. So the K-schemes kind of do that for us. So we're going to define 2 slopes. We're going to define an upwind slope, call it S minus, and that slope is going to be biased to the upwind direction. Okay? So it's going to take phi upwind, that's phi c, and phi far upwind, that's phi u. Okay? Maybe we should change the nomenclature and call this u and then uu. Maybe it's better that way. Anyway, so that's the upwind slope. And then we're going to pick a downwind slope, call it S plus. And that is going to connect phi upwind and phi downwind. Okay? And then we're going to say that the value of phi, we're going to take these two slopes, and we're going to combine them somehow. Average or some coefficient, right? We're just going to combine them somehow, and we're going to determine the value of phi based on that average slope. And we're going to say that phi at the face is simply phi at the cell centroid plus delta x over 2 times whatever slope we're going to choose for the variation of phi. Remember, we can do whatever we want for the profile assumption of phi, because we're only advancing the average value. We're not saying anything about how the actual value changes within the control volume. We actually don't know that information. That's like a subgrid model. That's a model that is inside the grid, subgrid. You know, it's just a model for phi, for how it changes. Okay, and then we're going to say, okay, what is that slope S? It's some combination of S upwind and S downwind. Okay, and such that if we choose k equal 1, we're going to be downwinded, and if k equal minus 1, we're going to be upwinded. So that makes sense, the minus sign. S minus is the upwind direction, and S plus is the downwind direction. So k equal plus 1 is going to give you the downwind direction. K equal minus 1 is going to give you the upwind direction. When you put these together, something beautiful happens. You put all of this information together. You can calculate the phi value at the face, and it's going to look, in the end, forgetting about I and j, phi at the face is going to be equal phi upwind plus 1 minus k over 4, phi upwind minus phi far upwind, plus 1 plus k over 4, phi downwind minus phi upwind. That's it. That's what you're going to implement. Okay? Now, something magical happens. When k equal minus 1, you get the second order upwind scheme. When k equals 0, you get the from scheme. When k equal half, you get the quick. An even higher order, right? Fourth order. When k is 1/3, you get the third order upwind scheme. Okay, that's even higher order than second order. When you put k equal 1, you get the center scheme. Let's try k equal 1. If k equal 1, this guy disappears, and then you get 2 over 4. That's 1 over 2. Yes. So and then 1 over 2. 1 minus 1 over 2 phi c is going to give you 1 over 2 phi c. That gives you 1 over 2 phi upwind plus phi downwind over 2. That's the central scheme. So what I actually implement in practice is the k scheme, okay, and change k as needed. All right. So in practice, I may give you an advection equation with a constant speed. C is positive, and you're solving phi t is equal to minus c phi x. Okay. So you do the integration. This is just a forward Euler, not in practice. You're going to need to do a second order approximation. But anyway, these are the indices. If you put I, so if the velocity is in this direction, this is upwind, far upwind. This is I plus 1, I minus 1, and this is I plus half. And you plug in the numbers, and this is what you get. Now, if you swap the velocity, the k scheme still works, our formulation, because we only formulated it in terms of upwind and downwind. And magically, the plus and minus signs, they just work. Because one argument you could say, well, in this drawing, okay, in this drawing, you said, well, phi f is phi upwind plus h over 2 times the slope. Well, what if you are in this direction? It's going to be phi upwind minus delta x over 2. Okay, but it turns out that doesn't matter, right? Because if you do that exercise, you're going to end up with exactly the same results, because the slopes are going to balance things out, because the slopes are defined in terms of upwind and downwind. Okay, I leave that to you as an exercise to prove it yourself. Okay. Now, I went ahead and implemented this. We'll see if we have time at the end. We can do it together. But for k equals 0, that's the from scheme. This is what you get. You get diffusion But you get this annoying dispersion at the end, right? For k equal, that's the third order upwind, you get this dispersion. For 0.5, that's the quick scheme, you get also dispersion. But then for k equal -1, so all we're doing is just moving the dispersion from one place to another, okay, moving the oscillations. And we don't like these oscillations, okay? We don't like the diffusion either, all right? So all of these higher order schemes, okay, they give you maybe better accuracy compared to the upwind, but they are oscillatory. There's no way to get rid of these oscillations. And even if you go like 10th order, you're gonna do even more oscillations. So the observation is that low order schemes are dissipative, but they don't oscillate. They preserve what we call monotonicity, which we're going to define in a second. And high order schemes are more accurate, but they are dispersive in nature. Okay? So can we make sense of that? Yes. There's actually this guy called Sergei Godunov, who during his PhD in around 1959, 1958, he came up with this theorem. That's Sergei Godunov. Looks like, you know, I don't know, that picture is like, looks weird. He's like, but he's still alive, this guy, genius. His theorem says that, I like this formulation, monotone behavior of a numerical solution cannot be assured for linear schemes with more than first order accuracy. So think of monotone behavior as you're not creating new minima or new maxima. So if you have a shock, you're not going to create a value. If the shock goes from 1 to 0, you're not going to create values above 1 or values less than 0. In other words, you're not going to be dispersive, okay, and create new minima and maxima. You want to assure monotone behavior. That's monotone behavior. And what that's his PhD. His PhD says, his theorem says, that you cannot preserve monotonicity with anything, for linear schemes, with anything higher than first order. So you can only do upwinding, just the upwind, first order upwind, if you want to maintain monotonicity. Otherwise, you are guaranteed to have oscillations. So we're talking about pure advection, okay? So what's monotonicity? Visually, these are monotone functions. And the formal definition is that a monotonically decreasing function is such that if x is less than y, then f of x is less than f of y, and the order is preserved, order of x and y, f of x and f of y. And a monotonically increasing function is such that if x is greater than y, then f of y is greater than x, f of x. But non-monotonic is something like this, where you can, you pick x and y, and then, you can't, your function is not for all x and y, your function is not continuously maintaining the order or reversing the order correctly, okay? I do have a proof of Godunov's theorem. I don't know how elegant the proof is, but it's pretty simple. It was developed by Philip Rowe, kind of in a note, and I take it from the former editor of the Journal of Computational Physics, Gretar Tryggvason. So here's some nice illustration of it. So this is going to take us as an aside. If you enjoy mathematics and mathematical proofs, this may be fun to you. Otherwise, don't worry about it. Take the theorem. You can use it as a tool and just use it, anytime you need it. All right. So the formulation goes like this. There's no animations in these next few slides, but we start with the simple advection equation, d phi dt equal minus u d phi dx, and we know from the continuous form that phi tt is actually u squared phi xx. There's a typo over here. Now, a general discretization scheme, whether implicit or explicit, think of just an explicit scheme right now, can be written as phi n plus 1 is some summation of coefficients times phi n at different points in space, I plus 1, I minus 1, I plus 2, I minus 2, I, etc. So take, for example, the simple forward Euler scheme. You have three coefficients over here, C0 and C1 and C minus 1. Okay, and the coefficients are 1 and minus u dt over dx and plus u dt over dx. So just I want you to agree that we can, in general, write a time integration scheme for this guy as such. Okay. So phi n plus 1 is some linear combination of phi n and the values on the grid. Okay, so next we're going to expand phi I plus k around phi I. Remember, k is just an index that's I plus 1 or I minus 1, right? So phi I plus k is phi I plus k delta x, which is h, d phi dx at point, this is point I, again another typo, plus k squared h squared over 2, second derivative plus order h cubed. So that's local order, locally second order. So what I'm going to do, I'm going to expand the n plus 1 derivative and the I plus k, sorry, the n plus 1 value and the I plus k value up to second order accuracy. So I'm going to neglect terms of order h cubed. So because I want to prove the theorem for at least second order accuracy. Okay? All right. So if you substitute this into that guy, you get phi I n times sum ck, and then h times k phi x, h times sum ck times k times phi x, right? Plus, you take this term and substitute it, and you get the k squared ck, right? And the h's and the derivatives come out. And so that gives us the right-hand side, an expansion for the right-hand side in space. Now, the next step is to expand the time derivative around n. So phi n plus 1 is phi n plus delta t d phi dt at n plus delta t squared over 2, second derivative in time at n, plus order delta t cubed. Remember, because we're going to stop, we're going to only take to second order terms. But remember that d phi dt is minus u d phi dx, and second derivative in time is u squared second derivative in space. So now we have space derivatives everywhere. Okay, it kind of reminds you of the modified equation. Okay, so now we're going to combine the two, and to assure order of accuracy, we want to equate all the terms. So we want to make sure that the first term, this sum ck, is equal, because these guys are equal, right? And if they're equal for arbitrary values of phi and delta x, then the coefficients need to be equal. So therefore, the coefficient of phi I n needs to be, they need to be equal. So this is 1 and this is sum ck. So sum ck equal 1. And for the coefficient of the first derivative, we have minus u delta t. That should be equal to h to sum, yes, to h sum k ck. Okay, right? So in other words, you divide by h, and same thing for the third term. You have h squared over 2 sum k squared ck should be equal to u squared delta t squared over delta x squared. Okay? Now, what does monotonicity imply? It implies that if phi I at n is greater than phi I minus 1 at n, so if one point is greater than the previous point, then at the next time step, if we want to preserve monotonicity, then phi I n plus 1 should also be greater than phi I minus 1 at n plus 1, right? So phi I n plus 1. So if these points are like this, next time step they're going to remain like this. We're preserving monotonicity. Or in other words, phi I n plus 1 minus phi I minus 1 n plus 1, the difference between two neighboring points is positive. In this case of monotonically increasing, you can take the same case for monotonically decreasing. Okay? But since phi I n plus 1 is sum ck phi I plus k, then the difference, right? So phi I plus 1 is, we're going to add a plus 1 over here. Then you get this difference is going to be equal to sum ck phi n at I plus k plus 1 minus phi n at I plus k. But we just assumed that the state at n is monotonically increasing. So this guy is positive, right? Okay. So what does this mean? We already assumed that these guys are positive. So therefore, the remaining condition to make sure that this whole thing is positive, right? Because we want this to be positive. So this whole thing has to be positive. We assume that these guys are positive. The only catch, the only remaining thing is to assume that ck is positive. Okay? We don't want any of these terms to be negative. Okay? So therefore, if ck is positive, for all k. Therefore, that implies monotonicity. Is this possible at all? And again, this is a simplified proof. Godunov's original proof is still understandable. You can find it on Wikipedia. It's not that bad. But this is just a simpler proof. Now, recall the order conditions, that some ck equal 1 and some k ck is minus the Courant number, and some k squared ck is u squared, etc. Now we're going to combine as the following. We notice that this guy is this guy times that guy squared. So in other words, this guy times that guy is equal to this guy squared. Okay, so some ck times some k squared ck is equal to this guy squared, right? Okay. So it's a little bit hand wavy over here, but it's an interesting theory. It's an interesting proof. So if you define, because ck is positive, we're going to define ck as ek squared and just substitute. So that gives you some ek squared times some k squared ek squared equals some k e squared squared. I'm getting to a form. I want to get to a form where I can write this as a vector product, okay? So if you take the vector A and call it E1, E2, all the way to Ek, and the vector B and call it Kek, then what do you have? You have A dot A. So prove it yourself. A dot A is this guy, and B dot B is this guy, right? That tells you that A dot A times B dot B is equal to A dot B squared all the time. But if you remember your vector calculus, the Cauchy, there's an inequality by Cauchy that says, well, actually, this is a very, very special case when they're equal. In reality, A dot A, B dot B is in generally greater than A dot B squared. And therefore, that's proof by contradiction, right? So what we set out to assume that, yes, this works, well, it's actually not possible. So Godunov shows that it's actually only possible when the Courant number is an integer. And we know that is not possible. Like in 2D, for example, you can't get to a Courant number, a global Courant number of 1. So you only can do 1/2, for example. Okay. So anyway, that's an interesting proof for Godunov's theorem. But the Godunov theorem is essentially a pessimistic prediction. Like, how can we get high order accuracy in space while preserving monotonicity? Can we ever do that? Okay. Well, we're doing numerical methods, so we can be very creative. There are two ways to address this. The first one is to say we're going to add artificial viscosity. We're going to artificially somehow add dissipation whenever we have an oscillation. So at the sharp gradient or at the sharp interface of a shock, we're going to start seeing this dispersion. Let's kill that dispersion by adding dissipation that somehow is proportional to the gradient. And we'll see how we do that. And the other one is use nonlinear schemes. And I have this, what? What do you mean, nonlinear scheme? Well, remember, Godunov's theorem is only pessimistic for, the keyword in Godunov's theorem is linear schemes, where you have this nice linear combination of phi n plus 1 and phi n. It's not weird, it's just a simple linear combination. But it only applies for a linear discretization. Can we do nonlinear discretization? We're gonna learn how to do that, okay? And that is gonna be your flux limiters. It's a nonlinear tool that changes nonlinearly in such a way to prevent these oscillations. So today we're gonna touch only on artificial viscosity. And what we're gonna do, we're gonna take this conservation form and change the flux, okay, and introduce a dissipation term. Now remember, this flux goes into a derivative, so there's a divergence here, div of f. So if you add a derivative to f, that is going to result in a second derivative for the global function, which is dissipative, okay? So if the flux has a first derivative, the resulting effect is a dissipative effect. But we want to choose this artificial dissipation in a way that only acts near oscillations, okay? And the way we do this is we scale this derivative by a magnitude of the gradient, the magnitude of the gradient. So we're going to detect when the gradient is high, we're going to add a lot of dissipation. When the gradient is low or all the way 0, we're not going to do anything. Okay, so that's why we scale the diffusion coefficient or the diffusion term. The coefficient of the diffusion term is proportional to the magnitude of the gradient at any given point. Okay, so that lets us turn on diffusion where the gradient is high and turn it off where it's low. So you can actually plot this, take a function and plot this coefficient and see its value shoot up whenever you have a high gradient and then go to 0. So because we want to preserve advection everywhere else, even in high order scheme, but we just want to dissipate the oscillations near the sharp gradients. And then you plug this in, and this is designed in such a way it also has, pardon me, a delta x squared involved, so that as the grid spacing goes to 0, we're going to be consistent with the original differential equation. That term goes to 0. So I'll show you some results with the Lax-Wendroff applied on this function. See what happens? So this is with a diffusion coefficient of 0.005. You get some oscillations over here, but they're much better compared to the original. So messed up the exact solution over here.